TNB coordinate system consists of three axes: tangent, normal, and binormal. We can draw a curve, what is a trajectory of a point, of a particle. The particle has mass m. So then we can draw a tangent at this point to the trajectory. So this is tangent line. And we can find also center of oscillation. And this is radius of oscillation. So that line is then normal line. And it is perpendicular to tangent line. Perpendicular to both, it is binormal line. So there is a right angle and there is a right angle. Okay? Unit vectors belonging to this system are unit vector of tangent, unit vector of normal, and unit vector of binormal. So we get three base vectors T, N, B. We can draw acceleration vectors. If we consider that particle accelerates during the motion, so there will be tangent component of acceleration and there will be normal component of acceleration. This coordinate system, this is the only one which is moving with particle. And this system is designed in this way that in binormal there is no acceleration. So total acceleration consists of tangent and normal component. Binormal acceleration doesn't exist. And if some particle accelerates, so probably there is some force, external force acting to the particle. It is given by components. So external force consists of tangent, normal, and binormal components. Okay, so I can draw it here. This is a tangent component, normal component, and binormal component. Now we can write a vector equation of dynamic equilibrium. Generally, it is that sum all forces plus inertia force is equal to 0. And what about inertia force. D'Alembert's force, inertia force, acts against positively oriented acceleration. In this case, it means that in tangent we have tangent component and normal component. If we use a basic definition for inertia force in D'Alembert's approach, so we can write that D'Alembert's approach is minus A by M, and because acceleration is definite by its components, so we can substitute it here and multiply like this. Okay, so this is tangent component of D'Alembert force, and this is normal component of D'Alembert force, so it is dt plus dn. This force, this inertia force, D'Alembert's force, is called centrifugal force, and this acceleration is called centripetal acceleration. Now we can expand. Now we can write component equations. First, second, and third, 4 directions of tangent, normal, and binormal. So in tangent direction we can write that the sum of all forces in tangent direction minus dt is equal to 0. Sum of all forces acting in normal direction minus dn is equal to 0, and sum of all forces in binormal direction is equal to 0. So in binormal direction there is resulting force sum F E B equal 0. So if there is no force, there is no acceleration in binormal direction. This is a feature of this coordinate system TNB. And how to calculate acceleration components. So AT is derivative of velocity in time. We can draw velocity in tangent line. Velocity lays only on tangent every time, in all cases. And normal component is equal v square over rho, where rho is a radius of curvature.